Welcome to The Explainer. Ever wonder what's actually going on inside an artificial intelligence's head when it's crushing a game of chess or solving a massive logic puzzle? Well, today we are cracking open the digital brain to find out. It is a wildly fascinating journey through strategy, logic, and extreme optimization.
Okay, let's dive into this. Think about a super dynamic environment, like a fiercely competitive soccer match. You've got all these players acting in real time, right? But crucially, their goals are in total, direct conflict. If one team scores, the other team inherently fails. To us, it's just a fun sport, but to an AI, this is a brilliant, profoundly mathematical scenario.
We actually call this an adversarial search. Essentially, it's a multi-agent competitive environment. You've got players with totally conflicting goals, and they're all exploring the exact same search space, trying to find a winning solution. In the AI world, researchers literally just call these problems games. And honestly, games are the perfect test lab. They give us a clear, measurable way to pit a computer's reasoning directly against human intelligence.
So here's our strategy playbook for this explainer. We're going to hit 5 main levels today. We'll start with the arena, then move to the pruners, check out the modern mastermind, introduce the wildcard, and finally wrap up with the rule followers.
All right, level 1, the arena. Let's map out the moves.
When an AI looks at a classic game like tic-tac-toe, it absolutely does not see X's and O's. Instead, it visualizes a massive, branching game tree. It starts at an initial state, plots out a sequence of legal moves, and traces them all the way down to a terminal test, basically the end of the game. At the very bottom, those leaf nodes get a numeric utility value. Usually it's a +1 for a win and a -1 for a loss. The AI casts itself as the max player, right? It's trying to maximize that payout. And it assumes its opponent is the min player, who's doing everything possible to force a low score. But here is the massive catch. Mapping out every single possible move takes way too much computing power. So how on earth does the AI avoid just completely freezing up?
Well, that brings us to level 2, the pruners. It's all about thinking efficiently using something called alpha-beta pruning.
Now, what's really interesting about this is how the AI sets up mental boundaries, so it doesn't have to check endless paths. It uses 2 key values. Alpha is the highest value choice it's found so far for the max player, and that initially starts way down at -infinity. Then you have beta, which is the lowest value choice for the min player, starting at +infinity. As the AI searches, it constantly passes these alpha and beta values down the tree to the child node.
Let's track the logic down the left side here. The AI does a depth-first search, diving all the way down until it hits node D, where it evaluates the terminal values, a 2 and a 3. Now remember, node B is the min player. It desperately wants the lowest score, but its choices are coming from max nodes underneath it, so it has to look at the highest of those lower options. Node D returns a 3, so boom, the min node instantly updates its beta value to 3.
And right here, this is the total aha moment. The AI moves over to branch E and evaluates the very first terminal node, which is a 5. Now, stop and think about it. Node B is our min player, wanting the lowest number possible. It already has a guaranteed 3 sitting there from branch D. Since 5 is obviously worse for min than 3, min is literally never going to choose branch E. So the AI just instantly stops looking down that path. It completely skips or prunes the next number, which happens to be a 9. It just doesn't even calculate it. Save time.
Okay, so the AI jumps over to the right side of the tree. Node A, the max player at the top, updates its alpha value to 3 because, hey, it knows it has a guaranteed score of at least 3 from the left side. It travels down the right, hits node F, and finds a 1. Because the min node C is going to pick the lowest value, beta becomes 1. But wait, max already secured a guaranteed 3 back on the left side of the board. Since this entire right side is going to yield a 1 or something even worse, max instantly knows this whole right branch is completely useless. It aggressively prunes node G and never even bothers checking the 7 and the 5.
And this brilliantly illustrates the final optimized path. You can see how the AI perfectly predicts the absolute best move, which is node D, while skipping a bunch of totally unnecessary math. It's so elegant. But there's a catch. Some games are just so massively vast that even the most brilliant pruning algorithms completely choke.
Which naturally levels us up to level 3, modern mastermind. Enter the Monte Carlo tree search.
So when things get incredibly complex, Monte Carlo methods step in with probabilistic, heuristic-driven searches. It's essentially combining that classic tree search logic we just talked about with modern machine learning principles. It breaks down into 4 really distinct steps.
selection, expansion, simulation, and backpropagation.
It works like a continuous loop. The AI selects a node, expands the tree to try out a new move, and then runs this incredibly rapid probabilistic simulation to guess the final outcome. Finally, it backpropagates, or sends that result all the way back up the tree to update the node's value. This exact reinforcement learning loop just repeats and repeats. And guys, this is the very engine powering absolute titans like AlphaGo Zero. It's how it mastered the impossibly complex game of Go. But what happens when a game isn't perfectly predictable? Like, what happens when we introduce luck?
Let's find out in Level 4, the wild card, stochastic games and the element of luck.
All right, so a stochastic game is essentially a repeated game, but with probabilistic transitions. Think of those beautifully unpredictable setups like Ludo, backgammon, or your favorite card game. You have to roll a die or draw a totally random hand. The final outcome absolutely depends on your strategic skill, sure, but it also relies heavily on pure, unfiltered chance. In AI research circles, they actually call this a 2.5-player game, with that wild half player being luck itself.
To handle this, the AI actually has to modify its entire game tree. It adds in these special chance nodes. Instead of having a definitive max or min move, the AI has to calculate an expected value based on the probabilities of what might happen. So if it's a literal coin flip, it assigns a 50-50 probability, a 0.5, to the branches and calculates a weighted average. The AI is, quite literally, doing the math on luck. Kind of mind-blowing, right? But what if we just step away from competitive opponents entirely? That brings us to our final stage, Level 5, the rule followers. Let's talk about constraint satisfaction problems.
A constraint satisfaction problem, or CSP for short, is all about solving a puzzle under very strict logical boundaries. You've got a set of variables, the domains where those variables live, and a strict set of constraints they absolutely must follow. Take a classic example like graph coloring. The AI's job is to fill in a bunch of shapes, right? But the ironclad constraint is that no adjacent sides can share the same color. By using a clever backtracking search, the AI assigns colors one variable at a time, and the second it runs out of legal values, it instantly backtracks and tries another route.
And you actually interact with these algorithms way more than you probably realize. CSPs are the engines behind our everyday logic puzzles. When you sit down to play Sudoku and, inevitably get frustrated and start erasing all your numbers, an AI just looks at it and sees 81 variables, strictly constrained so no number repeats in a row or column. It's the exact same logic computers use to solve the n-queens problem on a chessboard, mathematically ensuring that no single queen overlaps in an attack line. Let's move to one final constraint puzzle to really see how this builds. Imagine a cryptorithmetic problem, like where the letters SEND plus MORE equals MONEY. Through a process called constraint propagation, the AI uses the basic rules of addition and carryovers to infer exactly which letters must represent which numbers. It systematically narrows down the legal values for one variable, which instantly restricts the values for the next one, solving the entire math equation using pure, beautiful logical inference. Which actually brings us to our final and maybe most important takeaway. Beyond the game, let's look at real-world problem solving.
So why does any of this actually matter outside of an isolated computer lab? Well, because mastering a digital game tree is really just a practice run for the real world. A phenomenal case study here is machine learning at Google. They are utilizing these exact underlying algorithms, optimizing maximum utility, predicting those stochastic probabilities we talked about, and strictly satisfying massive resource constraints to intelligently map out their energy grids and server loads. It's literally the logic paving the way for them to become a fully sustainable business.
And that leaves us with a pretty incredible thought to end on today. We've seen exactly how an AI maps the board, how it prunes away the dead ends, calculates the exact odds of luck, and strictly follows the rules to secure a victory. So, if these algorithms can master a dizzyingly complex game of Go or instantly crack a Sudoku puzzle with such flawless efficiency, what massive, complex, real-world puzzles are they going to untangle next? Thanks so much for joining this explainer and exploring the mind of a gaming AI with us. Keep questioning and keep learning.